Let's dive into the world of Python recursion. We'll explore what recursion is and how it uses the call stack to solve problems. Here's a sneak peek at a basic recursive function. It consists of a base case and a recursive case. We'll understand these concepts in detail as we proceed. Recursion is a programming technique where a function calls itself to solve a problem. Think of it as a set of Russian dolls, where each doll contains a smaller version of itself. Now, a recursive function must have two key components. Firstly, a base case. This is the condition that tells the function when to stop calling itself, preventing it from running indefinitely. Secondly, a recursive case, which is when the function continues to call itself with a modified input, gradually working towards the base case. Here is an example of factorial function. We will define factorial of 0 as 1, which is our base case. Otherwise, the function will call itself to calculate the factorial of n-1. To understand how recursion works, let's use the factorial function as an example. Suppose we want to calculate the factorial of 3. The function factorial of 3 will call factorial of 2, which in turn calls factorial of 1, and so on until it reaches the base case factorial of 0, which returns 1. The call stack keeps track of each of these function calls. As each function call completes, it returns its result to the calling function, until we finally get the factorial of 3. The call stack is a crucial part of how recursion works. It ensures that each function call is properly managed, and that the correct results are returned in the correct order. Each time a recursive function is called, a new frame is added to the call stack. The stack keeps track of where to return after each function call completes. Memory grows with the recursion depth as each call adds a new frame. It's important to be aware of stack overflow. This occurs when there are too many recursive calls without reaching a base case, exceeding the maximum recursion depth. Python has a limit to prevent this, typically around 1,000 calls. As you can see in the stack visualization, each call to the factorial function adds a new frame to the stack, with the base case at the bottom and the initial call at the top. Let's consider another example, the Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones. Here we have base cases. If n is less than or equal to 0, return 0. If n is equal to 1, return 1. Otherwise, the function will call itself to calculate the Fibonacci of n-1 plus Fibonacci of n-2. Notice the sequence. It starts with 0 and 1, and each subsequent number is the sum of the previous two. The tree diagram illustrates how the Fibonacci of 5 expands into multiple calls to Fibonacci of 4 and Fibonacci of 3, and so on. This leads to many redundant calculations, making the naive recursive approach inefficient. Let's talk about common pitfalls in recursion. First, missing a base case. Without a proper base case, your function will recurse indefinitely, leading to a stack overflow. Second, using an incorrect base case. The base case must handle the simplest form of the problem correctly to ensure the recursion stops at the right point. Third, writing inefficient recursive functions can lead to exponential time complexity, like in the naive Fibonacci implementation. Fourth, a stack overflow happens when there are too many recursive calls, exceeding Python's recursion limit. Always ensure your recursive functions have a proper base case and are designed to avoid unnecessary computations. Here in this slide, we can see the countdown function without the base case. So, always define a proper base case. Memoization is a technique where we store previously computed results to avoid redundant calculations. This can transform exponential time complexity to linear in many recursive algorithms. Memoization dramatically improves performance, reduces time complexity, trades memory for speed, and eliminates redundant calculations. Look at the code example to understand how the computed value is stored in memory. Here is an example of recursive binary search. Here's the code for a recursive binary search function. Binary search is an efficient algorithm for finding a target value within a sorted array. The function takes the array, the target value, and the low and high indices as input. The base case is when the low index is greater than the high index, indicating the element is not found, and it returns -1. Otherwise, it calculates the middle index and checks if the element at the middle index is equal to the target. Found, it returns the middle index. If the element at the middle index is greater than the target, it recursively calls binary search on the left half of the array. Otherwise, it calls binary search on the right half. Binary search has a time complexity of O log n, making it perfect for divide and conquer with recursion. The visualization shows how binary search works, discarding half of the search space at each step. Let's compare recursion and iteration. Recursion is elegant for problems with recursive structures like trees and graphs, and simplifies complex problems with a divide and conquer approach. However, it has higher memory overhead due to the call stack, and is limited by the maximum recursion depth. On the other hand, iteration is more memory efficient with no call stack overhead, often has faster execution time, and no recursion depth limitation. However, it can be more complex for certain problems. Both recursion and iteration have their strengths and weaknesses. The choice between them depends on the specific problem and the desired trade-offs between elegance, performance, and memory usage. Here is a summary of what we've covered. Remember these key concepts. Recursion, which is a function that calls itself. The base case, which specifies when to stop recursion. The call stack, the memory structure tracking recursive calls. And memoization, which is used to cache results to avoid redundant work. Use recursion for tree and graph traversal, divide and conquer algorithms, and problems with recursive structure. And always define a proper base case to prevent infinite recursion. Utilize memoization for overlapping subproblems. Consider iteration for performance-critical code. Be mindful of stack limits with deep recursion. Use tail recursion when possible, and test recursive functions with small inputs first. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.